Welcome back on this video series about neural networks and genetic algorithm. We have seen the theory behind it, how the gene environment works, and we previously made a neural network that can make a decision based on its observation. Now let's see how we can use the evolutionary algorithm to have a working neural network that has been bred and selected after multiple generations. If you do not remember the principle of evolutionary neural networks, it is quite easy. You run a bunch of simulation where your environment will give your agent a reward. A positive one means it succeeded, and a negative one, it did not. After running thousands of simulations, you can compare different networks, and some will get better values as a reward, and those are the ones you want to take to make new generation. By modifying them a bit, you hope the new snakes will be able to find a better solution. I made a video on that, and you can find the link in the description below. Okay. We need to give a reward to the neural networks, and we need to track what will be this reward. Let's take back the neural networks that we have here, and let's add a reward variable, like that we initialize at 0, that we can modify in the future. So def set reward, we'll take the self argument and the reward we want to apply as self.reward equals R. This way we will be able to apply the reward to any snakes who will finish all the different simulation, and we can compare then the total number of reward they get. For that we need multiple snakes, so we create a number of snakes variable that we will set to 200 to start with, and we create a farm of snakes that we can compare in the future. So for all the snakes in range number of snakes, we will create a big snake, the neural network, with the observation size. Please recall that we use here the observation size to initialize our first layer, or let's more say the weights of the first hidden layers. And next we add this snake to the farm. Okay, right now our farm is ready. We have the 200 snakes which are initialized, and we can now run a bunch of simulation with them. As you may see, however, every time we restart the environment, we get different conditions, and this can be a bias. So in order to reduce this bias, we will use the law of big number, trying to create a massive number of simulation. We are able from that to see that did we get the reward randomly, or did we learn some kind of pattern which can approach us from the reward and get it. To do that, we will create a def run simulation with the snake argument and the number of simulation we want. Let's start with 10. We'll define the total rewards as 0. This would be what we will apply right here with the set reward. And this is what will be updated with all the simulations. 4 in range number of simulations. We get the environment to be reset, and we save it in the observation variable. We create a done equals false variable, and while we did not finish this simulation, we will simply run with an observation dot, well, we have done that already. Yeah, here. We just take this so we can save everything, observation, reward if we finished or not, and the info, even if we won't use the info here. And just be sure that you have this reward variable which was added, because I'm using against the solution notebook that I put online on the GitHub. So if you're following with me, be careful about the reward. Also, in the previous part of the notebook, we were used to call nth.render. Here we will use a massive number of simulation, and we don't care about representing all the simulations we have. In order to avoid losing stupid time with that, we will not use nth.render. We will, however, save everything in a total reward variable by adding the reward. And doing this, the system will be able to update the total reward that we will need to affect to the snake. So snake.set reward, like this, to total reward. And also, because I want to be able to track the simulation, I will do a return total reward. And I'm pausing the video because I have seen a mistake I did while I was trying to upload on YouTube and mounting the video. The sample has not been replaced by the snake, which means that every time we run the simulation, we don't run it on the snake, but on the first sample we define in the beginning. What you need to do is simply correct sample by snake. And in the rest of this video, you will see that it will not have much impact because of the bad shape we have with the environment and that we need to modify it anyway. But if you're following with me, please correct it. And if you're just taking the genetic algorithm solution, you won't have any problem because this will have been corrected. Next, because we will run a lot of simulation, I will use the TQDM library. So if you're not familiar with TQDM, just pip install TQDM. And what this will do is being able to show a nice progress bar. I will show you how it works. It's quite easy. We create a for loop, so for I in range 2000. I want to just run a simulation. So run simulation of of farm 0. So the first element we have here. And if I run that, I won't be able to follow anything until it's finished. To avoid that problem, I can use TQDM as import TQDM. And since I'm working with a notebook, there is a better way to work with. Do not type what I'm doing now if you're working on PyCharm or that kind of stuff. But what you can do is simply from TQDM import TQDM notebook as TQDM. And here I can just add this small function and I will be able to print the evolution of my simulations, which will be, I guess, some kind of good feedback for us to see if everything is going well, or if we have some errors, which appears as I did when I prepared the notebook, you will be able to find maybe some coherence of where you have some problem with. Okay. We will next use all the different snakes we have in the farm, right here. So for S in TQDM farm, and just apply a simulation on them. Run simulation, S. And I want also to be able to track what is the distribution of my rewards. So let's start by creating a reward list. And let's add the result of the simulation, which will return the total rewards we got as a number of episodes, as rewards.happened with the brackets. Run simulation S. All of them have been executed. That's perfect. And I can now plot the distribution. So hist rewards bins equals 200. And I will simply use this. Okay. I see I have most of them, like on the 10 simulation they had, they just fail every time. Here I have one good answer, which means I got a -8 as a total reward. I got 2. And here I got 3 different ones. What I can do next is taking a part of them in order to breed. So I would prefer to take this part of the farm than the one which fails every time, because I want to be able to breed more and more efficient one. Therefore, I create percentage saved variable, which means I want to keep 10% of the best snakes I have. And also I will create a chances of mutation, which means that every time I'm breeding from a previous snake, I want that each neuron has a very low possibility to have a mutation. we will get back to this in a few minutes. And we will use it as 1 exponent minus 2. Okay? We will save this, of course. And next, we will order the form we have to split it in an easier way. Because right now, if I take the form 0, and I get its reward, of course, I get minus 8, which means the first one we got the simulation had a total of 1 correct episode where it took the fruit. What I want is having the best at the first and the worst at the end. To do this, we'll use form.sort as a key, the lambda snake. We'll consider the snake.reward, and we reverse equals true to have the highest value at the beginning. And if I'm running right now with my form 0.reward, I should obtain this minus 4. Yeah, it's correct. And the minus 1 should give me a 10. Yeah, minus 10, sorry. Okay. Now let's work a bit on the mutation of our neural network. We have correctly ordered them. Now we need to be able to mutate the best. Then I take my neural networks and we will run on the mutate function. First off, we want to create a new object that will be returned, which means a snake. So I can start by creating a new snake variable, which will be equals to a neural network. And as parameter of this neural network, I want to recuperate the observation space I have here. And this is very easy. This comes from the self.layers 0, because this was the first layer. And if you look, it is recorded in the entry size, which means shape 1. And with that, I am able to create a new neural network. Next, I will simply manage to copy the layers and the bias and of course the self output. This is, however, some problem we have, because if I run this, first I will recreate all of the different layers which are created as random before modifying them. When you run with artificial intelligence, everything is about time and efficiency, and this is not efficient. What I need to have is some kind of specific test, which, if it is true, will simply not execute this, and I will simply mark myself what are the layers in the mutate function. This function will be determined by a variable, which means is a copy, that I will pass as false. And if it is not a copy, I will run this as default. So every time I call my neural network just with the observation size, it initializes it normally. However, in the case of the mutate function, I will pass it here is a copy as true. And after, I will be able to initialize the different layers. And we will modify them as we register them in the new snake. For L in self.layers, we have random mutation probability, which will be equals to np.random.rand, and I will need to copy the size of the layer. And the principle will be exactly the same as we had a bias. We simply want to add some numbers on specific neuron. To perform this, we will create a random map of each neuron, and if this map passes the threshold, we will be able to affect the specific neuron by a random value. We will make it very clear as we go in the code. np.random.rand, and we need to get the shape at the beginning, and then the shape as output. Sorry, shape as input, shape as output. Next, we want to apply this random mutation with a mask as np.where, and if our random mutation probabilities is under a threshold of my chances of mutation that I define right here, I am able then to apply a specific np.random.rand. And next, I will apply to a new layer the L plus random mutation props. And next, I will of course add this new layer to the new snake.layers. We will do exactly the same for the biases. Except that we need to take back the biases size. Here we can put 1 because we will always have 1 as input. And we apply again here the new biases. So new bias, which would be B plus the mask we apply, and the new snake. In the biases variable, we append the new bias. Let's make it a bit clearer. As an example, I created this demo matrix, which is a 10 by 10 matrix. We have random values from 0 to 1. Our objective is to slightly modify the matrix, but not too much. We will reuse this function of random props, which will be able at first to create a new matrix of the same size. So I will use demo matrix right here. It will be a 10 by 10. And my objective is to see if some of them are under 0.01. Right here, I have this one, which should be okay. What I do next is simply applying a mask, and if I am under the chance of mutation, which means under 0.01, like I have here, I will create a new random number that I will add to my demo matrix. Otherwise, I will simply add 0. And I can here print the results. Like that. And we see here that we will simply add this value, which is a big value, to our demo matrix. Like that. And we had here demo matrix, we reuse what we have, and we add the small modification. I will separate them so we can see it better. Like that. And I will print it next. We see here we have everything which matches, except here where we have added the number to the weight. Adding a big value has some problems, however, and we cannot use simply np.random.rand. We need for that to modify this element. Because what about creating negative value, as if you have some specific signals like you're going to the tail, don't bite it, we need to add negative value. To create negative values, we can simply use minus 0.5. And this will be very efficient to decrease our minimum value to minus 0.5 and our maximum value to 0.5. And even with that, it is a bit too much a modification, because if you change too much what you have in the neural network, you will not be able to keep the information as you had before. So we want to have small neurons modified and not from too much. This is the reason why I also divide by 2 here. And this is the formula we will reuse in the neural network. We don't forget otherwise to replace it by 0. So we will add 0 with that. And the same here. Also, we need to apply the same kind of mutation to our output, which is right here. And we will simply reuse what we had right there as self.output, yes, shape 0, and otherwise it's a 4 we have. But we can also reuse the same strategy we used here in case we transform this algorithm for other environments. Let's just retake the shape we had before. And next, we simply add to self-output the mutations we wanted. And this is a mistake because it's not the output of the main we want to change, it's the output of the new snakes. Don't make the mistake as I did. Here it is. Now we will create, well, we'll first clean what we have in the notebook, edit, delete cells, delete cells, delete cells, and here I will create a restart simulation function, because every time we will modify these neural networks, we will need to recreate the snakes, as they would not have all the kind of nice function we write. To do it, for s in farm, I remove them, del s farm equals list, and for in range number of snakes, we will recreate a neural network passing the observation size and adding it to the farm. Okay, next we can restart a simulation. So if we take farm 0.layers 0, I will print it, and let's simply restart a simulation and print this right after. Oh, yes, we need to use a global farm, obviously, because we are changing a global variable. And we see here that we correctly changed what we have in the first layer. It is a totally different layer. It's perfect. Okay. Next, we'll create a dev run global simulation to launch all our simulation in a single call. We reuse the global farm. We consider the rewards because we want to track how did each simulation, as we had before when we plot this histogram. And next, for s in tqdm farm, I want my rewards to append the run simulation of s, but also I want to display the histogram, which means what I would have for rewards. This way I can capture, because remember, run simulation returns the total reward of our sample, so I can plot the distribution I have here, plt.show, to display all of them. And next, I will sort with the same function we created here. And next, I will return the best snake I have with this reward. Okay, let's restart the simulation and let's run a global simulation. It looks nice. However, with the beans, we do not see much, so we will just add beans equals 200 here. Yeah, I prefer. It looks better. Okay, next we have here made a simulation which runs on all the farm. In other terms, this is what you create for each generation. We need now to call a Darwin cleaner, which will remove all the bad species we have here and we don't care about, to create also new species that can reproduce and create a better farm. As a beginning, everything is random, but progressively, sometimes it will find one solution, and with one solution, it will be able to transmit this to the other samples, and it can be reused and reused and reused over the time. It can learn new behavior, still keeping the former. So let's create our Darwin cleaner. We retake global farm, and we want to keep some parts. So we define what is the number of snake we want to keep. So quantity to keep equals, it must be an invariable. We can take half a snake. The percentage saved that we defined before right here. So we want to keep 10% of the best snakes multiplied by the length of the farm. we'll create a new farm, which is in fact the farm which is cleaned, so everything up to the quantity to keep. And since we will call Darwin cleaner after we organize the farm, which means like we only keep the good species, we will also create new species, which will be the next generation in list. And for E in range of len of farm minus quantity to keep, because I want to keep a farm size of only 200 members, I will take the father snake that will next create a new snake, my father snake dot mutate. And for my father snake, I could simply take the first one, the best one, and take him as the breeder for the whole new generation. This system would be, however, quite inefficient if you have one very lucky snake in all kind of simulation you got, because you have a random initialization at the beginning, where it would be able to have all the fruit in front of him and not having really learned anything. So what I want is to take from all the 10% I have every time the same number of elements. So new farm, which means the farm cleaned. I will take E modulo quantity to keep. And this way, I would have the first one will give breed as a father snake, next the second, the third, and so on. And next I reach the quantity to keep, which means 20, 10% of 220. When I will reach the 20th, I will restart at the first snake as 0. Next, I will add this new snake to the new species, this new species that happened new snake. Next, I will add to my farm what I have of the farm cleaned plus the new species which were created. I will try to run the Darwin cleaner, and everything was breeded and cleaned. Next, I will run a bunch of simulation where I will use, let's say, 15 generations, and I want to be able to run global simulation every time. Next, a Darwin cleaner. And to be able to follow what's going on, I will also create a rewards list. Rewards equals like that. And I will next plot the evolution of the reward. Like that. If I do that, I will have a lot of different noise because my run global simulation, if you recall correctly, if I remember, well, right here, it already has a TQDM and it already plot the histogram. What I can do is simply create some new kind of variable as initialization, which means display TQDM equals true by default. Display graph equals true. And I will make a condition, so if display TQDM like that, otherwise run it without the TQDM. And the same for the display graph. If display graph, I can do it like that. Okay. Yeah, missing this. And here I will run it as false, false. And I have a mistake because my snake is not correctly initializing. It means our mutate function is not working properly, or what we do with that is yes, because the mutate function did not return the new snake. So next we will also have return new snake. We need to restart the simulation because we restarted everything. Okay, restart simulation. And next I can run this. And here I'm at generation 3, 4, 5, 6, and so on. And it will be able after to print me all the rewards I want. And this is what we obtain, which is very disappointing because at the best, we do not see any evolution. It looks like only some kind of noise. This is linked to multiple things that we will see in the next videos, which are the number of dimensions we have, which is very high, and we can maybe reduce that, which is the absence of normalization, lack of clear information even from the dimensions, and we have also bad reward shipping. And also we could maybe use more snakes and more epochs. In the next video, we work on the dimensionality prediction, so stay tuned and thanks for watching.